In this video we're going to look at a detail of p-n junction operation, which is that the width of the depletion region changes when the bias applied to a junction is changed. This changing depletion width affects the current in bipolar junction transistors, so we'll modify our IV curves and our models to accommodate it. We talked about the width of depletion regions previously in sort of a passing way, because we mentioned that the charge in the P region of a semiconductor had to balance the charge in the N region of a semiconductor. That means the relative doping densities of the P and N region will change their relative widths. So high doping densities will result in short widths, while low doping densities will result in wide widths, because the total amount of charge has to be the same, and so low densities means you have to grab more space worth of charge. However, we haven't yet spoken about the total width of the depletion region. We can use constraints that are similar to charge balance, which are derived from the E field plot and the V field voltage plot here, to calculate the total width of the depletion region. And I've skipped straight past that derivation to the results at the bottom of the slide, which shows us the width of the depletion region in the N-type semiconductor and in the P-type semiconductor. And it expresses those in terms of Na, the number of acceptors, which is the number of dopants in the P-type region, Nd, the number of donors, which is the number of dopants in the N-type region, the permittivity of silicon, epsilon, the charge of an electron, Q, the built-in voltage, and the voltage applied to the junction Vd. Looking at these formulas, we can see that forward biases will reduce this term and this term, causing the depletion region to shrink, while reverse biases will increase both of those terms, causing the depletion region to grow. We also see that higher doping will shrink the depletion region because of this Na plus Nd term in the denominator of both expressions. These are great facts to remember, and I often do that by imagining like a forward bias squishing the depletion region together, like a forward bias is pushing it forward, which is physically inaccurate but helps me to remember what's going on. And so though that mnemonic is fun, having a physically accurate model to rederive these qualitative effects, forward bias and heavier doping shrinks the region while reverse bias grows it, is worthwhile. I think the electric field is the best way to make sort of a unified theory of these changes. And that's because the width of the depletion region determines the height of the peak E field. That's because integrating over the depletion region is how we make our E field curve. But that relation cuts the other way too. If you know the peak E field, then you have to know the depletion width, because E field is a one-to-one function with the charge that you integrate over. Forward bias reduces your peak E field, which implies that you have to have a narrower depletion region to produce the E peak. Reverse bias increases your peak E field, which implies that you have to have a wider depletion region to produce the E peak. Heavier doping on either side of the junction is trickier to model because it both increases the peak E field and the charge density on either side of the junction. However, it turns out the peak E field grows as the square root of doping density, while charge grows linearly with doping density. So the depletion width needs to shrink proportional to the square root of the doping density, which is what we see here. The collector-emitter voltage in a BJT in the forward active region can move around significantly without affecting the operation of the transistor. And that's captured by our large signal model over here, and by our semiconductor picture, where the collector-emitter voltage just needs to be high enough to keep the base collector junction reverse biased, so that we have drift across it. However, changing depletion widths on the BC junction could change our picture of how this works. In particular, when we change the depletion width on the BC junction, we move the edge of the depletion region away from where it is by default. So reverse bias will make the depletion region smaller, or the base smaller as the depletion region grows. And a forward bias will make the base larger as the depletion region shrinks. This affects the total current through the base, which is set by Fick's law as electrons diffuse from one side to the other. So we have the diffusivity of electrons times the rate of change of the concentration gradient. And base width modulation will affect, which is the term used to refer to changes in the length of the base as the bias on the collector base junction changes, will change the total size of dx, which in turn changes the current through our BJT. We can import that effect into our IC VBE curve as slight fluctuations in the exponential behavior as VCE is varied. So our exponent will be a little steeper or a little shallower as VCE changes. As usual though, we'll be able to get a better look at this behavior when we plot IC versus VCE, so that we don't have our changes swamped out by the big changing exponential with VBE. So here's our IC VCE curves, but with the base width modulation included. This results in a linear increase in current in the forward active region as VCE is increased. And I've exaggerated that pretty dramatically in this plot. These slopes are actually much steeper than you'd see on a real BJT curve. Often this increase is barely perceptible when you measure it. The IC VCE dependence is linear because the depletion width changes are small compared to the base. And so we can take a Taylor expansion of our currents dependence on this depletion width to show that the deviation is linear to a good approximation. One detail that might not be immediately obvious is that each of the slopes in the forward active regions points to the same intersection point at 0 minus VA. Excuse me, at minus VA, comma 0. That intersection point is called the early voltage, and it's usually in the range of 50 to 200 volts depending on the BJT. We can use the early voltage to modify our equation for collector current in the forward active region. This is pretty easy. We just multiply our existing collector current by the expression 1 plus VCE over VA, which creates a small linear dependence of current on VCE. This term will be important when we start making small signal models of the transistor. So in summary, changing the bias on the base collector junction will change the depletion width, and in turn the base width of a BJT. Changes in the base width create small changes in the collector current because the collector current is determined by Fick's law, which cares about the change in concentration divided by the change in displacement. These small changes in IC change the shape of our IV curves, most notably by adding a linear dependence of IC on VCE. And that linear dependence means that all IC VCE curves converge at a point 0 minus VA, which is called the early voltage. So VA describes the severity of base width modulation.